So now that we've talked about some of the parameters of phase and angles and waves and line lengths and all of that, let's get down to what we're here for. Let's talk about the formation of standing waves and how reflections are created and what they mean. So we're going to, again, start with our signal generator. In this case, our radio. I'm not even going to draw the impedance. I mean, you know it's a 50 ohm source. And it's going to be going into our coaxial line of some length. And finally into a load. Now, given that we know a line terminated in its characteristic impedance is not going to produce any reflections. So we're going to terminate this in 100 ohms. And we're going to use a full wave line again. And later we will use lines of other lengths, different lengths, to see how those how that works. So what's going to happen here is the signal is going to go out, and it's going to see a load that's too high. So at this end, we have we've measured our 10 volts of RF at this point. That's our initial level in the line. And at 50 ohms, that should be 200 milliamps. That's what should be flowing. This is what defines our characteristic impedance. Amps per volts, the ratio of amperage to voltage, and you can determine your characteristic impedance of your line, among other things. But when it gets out here, it's going to see 100 ohms. The 200 milliamps is not going to want to flow through 200 ohms. There's not enough voltage to push 200 milliamps. So one of two things are going to happen. The voltage has to go up, or the milliamps have to go down. So either we go to 20 volts, or we go to 100 milliamps. Well, a little bit of both occurs. But the voltage here does go up, and that's the significant factor. If the impedance is raised above the characteristic impedance, if the terminating impedance is too high, the voltage will rise. And that is the same, this is the interesting part, that has virtually the same effect as inserting a signal generator at the load end. So this excess of current producing an excess of voltage across 100 ohms is going to be as if a signal generator has been turned on and is sending a voltage back. The backward wave, as they say. Now, the interesting thing about the wave that's reflected back is that it's reflected back 180 degrees out of phase. So if we go 180 degrees away, right, we have a waveform at this point that would be going negative. 180 degrees from here, we're into a negative phase again. So that's what's being reflected back. So that little bit of voltage coming back is going to look like that. So what we end up with back at the source is we end up with a composite voltage, the standing wave, or a standing voltage wave, however you wish to describe it, that looks like this. It is the sum of the two. So we have our V forward, our standing wave, and our V reflected. Now the current is not reflected back 180 degrees out of phase. The current is reflected back in phase. So if this is my voltage. If I'll do a small one over here to show you the current. So the current starts out in phase with the voltage. So we have a nice current wave. And it's going to be reflected back starting where it's at, in phase. It's going to continue, and maybe a tiny bit of current will come back in phase. So the resultant waveform will be a little less. So here's our I reflected. Combining these two, we end up back here with a current in voltage which reflects the mismatch at the end, and it has changed not our characteristic impedance, but it has changed our input impedance. So the impedance seen by the generator now is no longer 50 ohms. I'll do my best to avoid some math, but we need to explain a few things here. One misconception to be dispelled is the standing wave ratio, or the standing wave SWR, is not the ratio of the mismatch to the generator. So let me run through that quickly. We're going to calculate the reflection coefficient equals the impedance of the load minus the characteristic impedance over the impedance of the load plus the characteristic impedance, which in this case equals 50 over 150 is 0.3. And the SWR, we can calculate from that, is the ratio of the forward plus the coefficient that's reflected, which is rho. I've also seen it as listed as gamma, and 1 minus the forward minus. So there's your ratio, which is 1 plus 0.3 is 1.3. 1 minus 0.3 is 0.7. And the standing wave ratio is 1.8 to 1. So there we go. Now, had this been the case where instead of 50 ohms we had, say, 25 ohms, we'd have a similar condition. These are absolute values, except in that case we would have a reflected current 180 degrees out of phase and a reflected voltage in phase 0 degrees. But the two key points I want to make here: A, is the forward and the components, regardless of anything else, the components of the reflected energy, meaning the voltage and the current, those two components, are always reflected back 180 degrees out of phase. It's a very important distinction, given the way we're going to be metering this. Second important point is the SWR is not the ratio of the impedances. And this issue gets even more complex when you get into phase shifts due to reactance. When you have inductance and capacitance in your load such that the voltages and currents are phase shifted, and those shifts are reflected back. So it gets much more complicated as far as what the actual standing wave ratio is. Suffice to say, the ultimate standing wave is the only signal that's in this line. If you look at this line, you're never going to see a forward wave and a backward wave. You can infer them by looking at the phase relationship between voltages and currents, or more, not so much the phase relationships, but using phase shifting techniques to measure the ratio of voltage to current, and you can determine what your forward and reflected components are. But ultimately, looking at this signal at any point in time, this is the only thing you're going to see at any given time is the standing wave. And yes, it is comprised of components of the initial signal going forward and some of that energy being reflected back, but you can't see those because that's the only thing that exists in that line. This is the sum of all the signals. If I had a tuning stub off of here, or if I had a T going off feeding a delay line for another antenna, say on a phased array, and that antenna had a problem and was contributing some reflected signal. All of the sum total of all the signals floating around, reflected, generated, what have you, all comprise one voltage and current. Ultimately, the standing wave. Now, they may not appear the same at all points on the line, but there's only one signal. That's an important distinction. That's very important to know when you're looking at these measurements. Okay. You can look more of this stuff up at your leisure if it helps you to understand it. But it's ratios. It's just ratios. Even the impedance of the line is just a ratio. Voltage to current. Well, that's pretty simple. That's just Ohm's law, right? I was going to change this to a half wave, but it actually comes back the same. It's 180 degrees and 180 degree long line. It's all 180 degrees. It all comes out the same. So multiples of a half wave. Whatever occurs at the end of the line is what you see at the input of the line. So let's do this. Let's do a quarter wave line. Now this is a special case. Quarter wave lines have always been used in radio work for impedance matching, for canceling signals, for use as filters, because they have a very interesting characteristic. They invert the impedance of whatever is at the end of the line. And because the line, this lambda is with respect to frequency, which means they have a frequency characteristic that is going to be unique for any given line. So let's do the quarter wave case. So here's our full wave. Quarter wave is right here, 90 degrees. Now I'm going to leave all this because we're going to need it. So I get out to the end of my line, and let's see, should I do a short or an open? I'll do an open this time. We'll do an open circuit. So my line is open. Z load equals infinity. Nothing there. Okay? When I get to the end of my line with my 10 volts and my 200 milliamps, what's going to happen? 200 milliamps has nowhere to go. Nowhere. It goes to zero. 200 milliamps cannot flow. It goes to zero. However, the voltage has no load now. The voltage is it's gonna jump. Voltage is going to rise considerably. So that's what's going to be reflected back. That voltage. The voltage reflected back is going to be 180 degrees out of phase with what appears at that end of the line. Well, 180 degrees out of phase is over here. It's negative and it's going positive. So it's coming back, it's negative, and it's going positive. What is my voltage at the input of the line? What does my generator see now? V forward, V reflected. What's the sum? V equals 0. The same thing occurs with the current. I have some current flowing at the beginning. And by the time it gets to the 90 degree point, it's 0. There's nothing coming back. 180 degrees later, what's coming back is rising. So my current, my net current, is very high. I reflected is, I'll just use a little up arrow. It's high. It's very high. So what does this see? It sees 0 volts and a very high current. It sees a dead short. A quarter wave inverts the open to a dead short. How is that useful? How can we use that? We can use that in a lot of different ways. But one way that we can use it, and I'm going to draw an antenna system. So here's our antenna. We'll make it a dipole. And I come down here, and here's my radio. Okay. And let's say this is my 10-meter antenna up here. And my neighbor comes over and he goes, "You're tearing up channel 2. I can't watch my news at night." And, well, why would you be on 10 meters at night? But anyway, I can't watch my news in the morning. I'm brushing my teeth. So what are you going to do about it? So you go into your shack and you cut a line, you do your calculations that a quarter wave, okay, at 56, it should be doing 54 actually, but we'll say 56 megahertz, okay, equals, well, you know, a half wave is going to be 492. So a quarter wave is going to be 246, 498, right? 246, I think it's 246. 246 times the velocity factor of the cable. I haven't talked about velocity factor yet, but I will. Times the velocity factor of the cable, which is in this case 0.66, because we're cheap and we're just buying RG8 standard stuff, divided by the frequency in megahertz. And the answer is, it's about 8 feet. 3 feet. So you cut a piece of cable 3 feet, you put a T connector in your line. Actually, you should put it at the transmitter. Really doesn't matter, but you should put it at the transmitter. And what you get is you get a notch at 56 megahertz. Yay! It's one problem. Quarter wave at 56 megahertz is 1/8 of a wave at 10 meters. So now you got this little 1/8 open circuit 1/8 on 10 meters. Oh, that's all bad. That's not going to work. Your SWR is through the roof. What am I going to do about that? Oh, what if I make it a quarter wave at 28 megahertz? I'll make it twice as long. And I'll make this a dead short. So now, at 28 megahertz, my dead short looks like an open circuit. It's all happy. 28 megahertz works fine. At 56 megahertz, I have a trap. Well, not a trap, but I have an attenuating signal. Does this work? Yeah, not bad. It's not perfect. You don't get complete attenuation. I mean, it's not going to see a dead short here. This is a half wave at 56 megahertz. In fact, you will see a little bit of that characteristic here. You will see a little dip where it's actually a half wave. It will come down a little lower. So the half wave at 56 shows a dead short. But a quarter wave at 28, the short looks like an open. Quarter waves. I'm giving you examples here. Because as soon as possible, I give you a concept, I want you to see it applied right away. The whole purpose here is to give you some sort of an innate sense of how this works. And I can't do that if you don't see examples. And I want to try to get away from the math. So I'm just throwing examples at you here. Okay, moving on. So the last example of how quarter wave sections and half wave sections, and just using, even, or I should say, odd, odd multiples of quarter waves, or even multiples of half waves, can be utilized in unique ways. It's a really fascinating property. Is the coaxial collinear antenna. And for those of you who have operated repeaters, one of the valuable characteristics of a good repeater system is that it is able to receive signals with a minimum of flutter and dealing with shadows and terrain, reflections in buildings, in urban environments, things like that. And the way that's achieved is an antenna that has good null fill. Now, a lot of people think gain is the most important characteristic of an antenna, but in this case, no. The gain of this antenna is about 9 dB. And this example that I'm going to show you was originally manufactured and popularized by the Phelps Dodge Corporation, which was a company that made copper tubing for the most part. They also made duplexers, good ones in fact. So they used the properties of coax to build an antenna which was very large for its gain. It did not have a very high size to gain ratio, and in the case of, you take something like a Hustler G7, okay, it's a relatively small antenna. It's got a lot of gain, projects a lot of a small beam width towards the horizon, but that doesn't have good null fill. This antenna, being 20 some feet tall, is a very big antenna. I think they were 23 feet or 21 feet. It's a lot of antenna. Has a very large aperture, and each antenna element has not as much of a decrease in radiating efficiency as you might suspect. Most antennas, as the signal travels along the antenna, the bulk of the signal is radiated from the lower portion where the current is high, and then as you reach the voltage node at the end, it diminishes. This antenna is not so much. This antenna has each half wave element contributes almost equally to establishing the field, and it has having such a large aperture, it's very good at null fill. And if you've listened to if you've operated repeater systems using a station master, you'll notice they do tend to have a little bit less picket fencing, a little less dropout. It's a good antenna. So here's how it works. It's really, I think, really kind of slick. We have a feed line of any length, 50 ohm feed line, doesn't matter what length it is. And the first thing we come into is a quarter wave matching section. So we have, here's our little lambda over 4, a little quarter wave section right there. That quarter wave section is fed normally, center conductor to center conductor. But at the other end of it, we swap them. This center conductor goes to the shield of the next section of coax, which is a half wave. The shield goes to the center conductor and is carried on to the next half wave. So this is a series of stacked half waves, and I think there's a lot of them. 7 or 9 or 8. Could even be more, as I don't recall. I only took one apart once. But there's a lot of them, and then actually there's as many as you want. I think there's a point of diminishing returns though. 9 dB is probably that point. So, and finally we have another half wave section. And each time we transition from one half wave to the next, we flip our feed. The center conductor becomes the shield becomes the center conductor. And by doing that, we achieve a 180 degrees phase shift. So each of these antenna sections, each of these half wave elements will have a similar, if this is the center of the dipole, each one will have a similar wavefront established on it. And by going through this quarter wave section, we have taken a current node and turned it into a voltage node. Because what do we know about quarter wave sections? Quarter wave sections invert the impedance seen at its opposite end. So if this is a voltage node at this point, obviously it has to be a voltage node, it's a half wave dipole. You take any dipole hanging in the air and it's connected to nothing out at the far end. So that has to be a voltage node. Can't be any current flowing in, there's nothing for it to flow in. So we want to convert this to a voltage node so that at the other end of the quarter wave input, it's a current node. So the coax is happy. We get to the next section and this voltage node is flipped to feed the next voltage node in opposite phase. But a voltage node at the other end of the half wave section is also a voltage node. Half wave sections don't flip impedance. So we have this repetition going on. When we get to the top of the antenna, which I've drawn over here, there's quite a few sections. We have the same situation. You have a half wave and a half wave and a half wave. I'm sorry. And a half wave. I've drawn the top section a little large. So lambda over 2, lambda over 2, lambda over 4. We have another quarter wave section. This quarter wave section is terminated in a dead short. A dead short is seen at the input to a quarter wave section as a voltage node. So again, we have a voltage node, we have a current induced by the half wave below it, we have a current flowing on the outside, which is continued in just a simple quarter wave wire. So we have another lambda over 4 piece of wire, which ends as would a normal any antenna, ending in a voltage node in free space. And that's the top of the antenna, and we're done. Now there's one thing that I've left out I want to come back to. There's no balancing going on here for any RF currents that may want to continue flowing on this shield connection and back down the coax. So what they've done is they've taken another quarter wave section. I can draw it in red. And connected the center conductor of that section to the feed point, or to the, what is essentially the voltage point feeding the antenna. And they've also connected it to ground. Well, we'd like to think of this as ground. What we want our zero current point to be. So again, we have a dead short. I'm sorry, I didn't show the dead short. We have a dead short here. The center conductor to ground. Center conductor to ground, and then connected to the ground of the input match. This dead short appears at this end as an open circuit. So no signal will be lost from this point into that section of coax. It just appears as an open. However, any current flowing on the shield, attempting to flow on the shield here, will induce a current flowing in the opposite way in the other shield of this section of coax. So this constitutes what looks like a piece of open wire line, a quarter wavelength long, which is open at the top. Being open at the top, it appears as a dead short at the bottom, which it is. So any current flowing down will see a dead short at this point and will not flow beyond that point. And so that is, they refer to that as a balun. It's unbalanced. The whole thing is unbalanced. Maybe it's an unbalanced to unbalanced. It's a trap. I don't know. But they refer to it as a balun. And that's the antenna. And it's all quarter wave and half wave sections. The only vagary here is, no matter what we do, the velocity factor of the exterior of the coax, the shield of this coax, is always going to have a velocity factor that's higher than that of the conductor inside. The coax's velocity factor is always going to be a smaller number. So it's crucial that the length of the coax account for its velocity factor in terms of transforming this 180 degrees. So we have to account for that, which means that the outside of the coax is going to be too short. It's actually going to be, it's going to resonate a little bit higher than the inside of the coax if you look at the frequency distribution. So there's a little tweaking, there's a compromise that needs to be met there. The 180 degrees is probably more important than having the outside of the coax being a little too short. But it works. There's plenty of formula on the internet to build these things. There's calculators to tell you what lengths to cut these. I needed a UHF repeater antenna in a hurry. We set up a temporary repeater site, and I said, let's build a coaxial collinear. We needed a big antenna. We need something with some gain. We wanted a decent antenna. Well, what does every ham have in his shack? Coax. So I basically took a bunch of coax and cut it up into little sections. I think they were about roughly about 7 inches long, and soldered them all together in this configuration, stuffed them inside a piece of PVC with a cap on the top, and up in the air it went. I think that antenna probably functions for several years and fabulously. I don't think we made any modifications to it, and I got the formula probably out of the book somewhere. That was actually before the days of the internet. So there you go, coaxial collinear. And we'll talk more about how collinears and what have you form wave fronts and beam fronts and stuff when we get into antennas. But for now, just the transmission line properties of this are just coax, just transmission line. Wouldn't you know it, battery on the receiver went dead this time because I failed to pay attention to the little blinking light.